Friends, in this video we are about to discuss the condition of equilibrium for a dipole. A very important concept, not just from the point of view of word, but also from the view of any competitive examination. In this video you will learn in what position of a dipole when placed in a uniform electric field can be termed as stable equilibrium or unstable equilibrium, in what situation the work will be done, and in what situation work will be obtained when we rotate a dipole in any uniform electric field, friends. So let's begin with this particular class, friends. Friends, as you all know, whenever a dipole is placed in any uniform electric field at making some angle theta with the electric field, then the dipole experiences a torque given by the expression Pe sin theta. And in this particular situation, when the dipole or the dipole moment or the axis of dipole makes an angle theta with the electric field, the potential energy of the dipole happens to be minus Pe cos theta. Let's discuss three different orientations for a dipole. The first orientation, in which theta is equals to 90 degree. That means the dipole is placed in such a manner that the dipole axis or the dipole moment vector makes an angle of 90 degree with the electric field. In this orientation, the torque experienced by the dipole happens to be the maximum torque, because the maximum value of sin theta or sin 90 degree is always 1. I believe you are well aware of the trigonometrical functions, and you know that sine and cos functions happens to be a bounded function whose values varies from -1 to +1. So the maximum value that the sine function can take happens to be +1, friends. So in this expression, the sine function has got a maximum value of 1, and that's why the torque experienced in this particular orientation happens to be maximum, and that happens to be Pe. So this is the maximum torque experienced by any dipole, and one should remember that at an angle of 90 degree the torque experienced by the dipole happens to be a maximum torque. Now suppose I place the dipole in an orientation, in a position where the dipole moment happens to be lying parallel with the electric field. Let's say like this. Now you can see the dipole moment vector happens to be parallel to the electric field vector, and then the torque experienced by the dipole will be equal to 0 Newton meter. Why? Because theta is 0, sin 0 is a 0 value, gives us a 0 value, and when I substitute the 0 in the above equation, the torque experienced will also be 0, friends. Now let's take another case when the dipole moment lies opposite to electric field vector. In this situation, the theta becomes 180 degree, and therefore when theta is 180 degrees, sin 180 degree is also 0, and so the torque experience in this situation also happens to be 0. Now if torque is 0, then the dipole itself comes under rotational equilibrium. So here, since torque is 0 in both the situation, I can say that the dipole is in rotational equilibrium. It can't rotate. It is in rotational equilibrium. Now, since the dipole is in rotational equilibrium, the dipole is not going to rotate presently. Now if you look about the force part, the negative charge experiences a force which is directed opposite to the electric field, whereas a positive charge experiences a force which is directed along the direction of electric field. Both forces are equal in magnitude with their line of action being same. Hence the net force also becomes 0. Since the net force is 0, therefore the dipole also comes in translatory equilibrium. That means dipole no longer can move or translate in the electric field. Hence it also comes in translatory equilibrium, friends. Now since the torque is also 0, force is also 0, being in both translatory as well as rotational equilibrium, I would use the term that the dipole is in equilibrium position, friends. Now the question that arises over here is whether this equilibrium is a stable equilibrium or whether this equilibrium is unstable equilibrium. So let's review, friends, what do we mean by stable equilibrium and what do we mean by unstable equilibrium. From mechanics, we know that equilibrium can be of two types, or rather three types: stable, unstable and neutral. Presently the neutral equilibrium is out of context, so let me not talk about the neutral equilibrium. Now you can see on the screen I have shown you two different positions of the blocks, 1 and 2. Out of these two positions, which one happens to be the stable equilibrium and which one happens to be unstable equilibrium? Let's discuss that particular point. Now what do we exactly mean when I say that the box is in stable equilibrium? So whenever I am talking about a stable equilibrium, it simply means if I disturb the block from its original position and release the box should come back to its original state. That is what I mean when I say about the stable equilibrium. And similarly, if I disturb the box from its original position and leave it, and if the box does not come back to its original state, that's what I mean by unstable equilibrium, friends. So let's review that situation. Suppose I topple the box from the state 1 or from the position 1. I tilt the box from state 1 to one end and leave it. Will the box, or does the box have the chances to return back to its original state? The answer is pretty less no. The chances of a box returning back to its state will be pretty less. It's not possible. Hence the state 1 becomes the state of unstable equilibrium. Now let's review the state 2. Suppose I lift the box and release it. What would happen to the box? Won't you feel that the box will return back to its original state? So that makes the box in the state 2 or in the position 2 to be under the state of stable equilibrium, friends. Hence I can say the state 1 as the state of unstable equilibrium, whereas state 2 as the state of stable equilibrium. Now if you also notice about the potential energy of the boxes in these two different states, which potential energy I am talking about? I am basically talking about the gravitational potential energy of the box, that is mgh. So look at this particular height h1 and look for this particular height h2. Out of these two heights, which one would you find larger? Definitely h1 is at a higher position. This happens to be my center of gravity of the box, friends. Isn't it? G. So potential energy in the state 1 is greater in comparison to potential energy of the state 2, and that gives me the hint about how to conclude which orientation represents the stable equilibrium or not. You should understand that whenever the body is in minimum potential energy state, that state of the body is going to be referred by us as the stable equilibrium state. So you can see over here the potential energy is minimum, hence this state represents the stable state of the equilibrium of the body. So in order to decide the stable or unstable state, we would always refer to the potential energy of the body in that particular state. In a stable equilibrium state, the potential energy will always be in a minimum value condition beta. So that's how we will judge whether the state is a stable equilibrium state or whether the state is unstable equilibrium state. Returning back to our dipole problem, friends. Here we need to discuss under which of the two orientation the dipole is in stable equilibrium and in which orientation the dipole is in unstable equilibrium, friends. Here we have got two particular state of the dipole, state 1 and state 2. Now, out of these two states, which one happens to be the stable equilibrium state and which one happens to be unstable equilibrium state? In both of these states, the net torque is 0 as well as net forces is also 0. The question now comes, which state represents the stable equilibrium state or which state represents the unstable equilibrium state? Just now we discussed that in case of stable equilibrium, the potential energy needs to be minimum. So if the potential energy is minimum, that state is going to be a stable state of the equilibrium, provided the net force and the net torque is 0. And the state in which the potential energy may be having some value apart from that minimum value, if it has some other value, that particular state will be the state of unstable equilibrium. Now we know in these two states the net force and the net torque is 0. Let's calculate the potential energy in both these states. Now you already know the potential energy formula happens to be minus Pe cos theta. In this case theta is 0. Substituting the value of theta in this particular equation of potential energy, you will find that potential energy comes out to be minus Pe as cos 0 is 1. Now let's also calculate the potential energy in the state 2 using the same equation, minus Pe cos theta. Here theta happens to be 180 degree and cos 180 degree happens to be minus 1. So the potential energy comes out to be plus Pe. Out of these two potential energy values, which one is minimum? Obviously minus Pe. That suggests us that whenever the theta is 0, this happens to be the state of stable equilibrium, and whenever theta happens to be 180 degree, that happens to be the state of unstable equilibrium. So if dipole moment happens to be parallel to the electric field, theta becomes 0, represents the state of stable equilibrium for dipole. Whereas if theta happens to be 180 degree, that means the dipole moment is directed opposite to the electric field vector. That represents the state of unstable equilibrium, friends. Summarizing the entire thing, thus potential energy of the dipole system is minimum whenever dipole moment is parallel to the electric field, as just now I told you, and in this situation theta becomes equals to 0, hence this corresponds to the stable equilibrium position. Whereas when theta was equal to 180 degree, that is when the dipole moment was opposite to the electric field vector, potential energy was not minimum, hence that position corresponds to unstable equilibrium position, friends. I hope this gives you an insight. When any numerical problem suggests you the dipole is in stable equilibrium or the dipole is unstable equilibrium, you would be able to find or understand in what orientation the dipole has been placed. Now let's understand how one can obtain the work or how work will be done in rotating the dipole, and in what orientation can we say that work has been obtained. Now let's refer to this first orientation or position of the dipole. Theta in this position happens to be 90 degree and the dipole is experiencing a maximum torque. Since the dipole is experiencing a maximum torque, and who's applying this torque? The torque has been applied by the electric field, and under the action of this torque, the dipole has a tendency to rotate, and the electric field will rotate the dipole and will try to bring the dipole back to the condition of stable equilibrium. It's something very similar. If you raise a ball from ground to a certain height and you release the ball from there, the gravitational force itself tries to bring the ball to a state where the potential energy becomes minimum or zero. And in that situation, if the reference point is taken as the ground, the ball comes back to the ground. So similarly over here, the torque applied by the electric field rotates the dipole and brings the dipole in the orientation of minimum potential energy, so that the dipole moment becomes parallel to the electric field. You just now have learned that the potential energy in this orientation happens to be minus PE. So in this situation, who does the work? Who is rotating the dipole? The electric field itself rotates the dipole, isn't it, friends? So when the electric field is rotating the dipole, so you are not going to do the work, rather work will be obtained. So that's why I am saying that if the dipole is placed perpendicular to the electric field, then field itself will bring the dipole in minimum potential energy condition, and thus work will now be obtained. Now, if you move the dipole from the condition of a stable equilibrium, that is the position in which the potential energy was minimum, to any of the orientation, you need to do the work. Now work will be done by the external force or the external agent or external torque. So suppose if from the orientation 1 I rotate the dipole in any other orientation, then work must be done, and that work done will always be stored in the form of potential energy of the dipole. So work done by the agent is equals to change in the potential energy of the system. So now what you need to do, you need to find out the change in the potential energy. You already know that in this state the potential energy was minus PE. Now from this state, in whatsoever the state you take the dipole, that potential energy, in that state the potential energy you should calculate and then find out the change. Change in physics always means final minus initial. Now remember, work done by the field is always negative times the work done by the agent. And what is the work done by the agent? Work done by the agent always happens to be the change in potential energy. So if the question is asking you to find out the work done by the field, then you should always find out the minus times the change in potential energy, and that work done by the field will always be the work that you are about to obtain. And remember, whenever the work has been done by the external agent, that is what in physics always is going to mean as work done. So whenever you are required to find out the work done, look for the change in potential energy. Whenever you are required to find out work obtained, look for minus change in potential energy, friends. So that's what let's conclude it out. Work done by the agent is always going to be equal to the work done, whereas work done by the field will always be the work obtained. So while referring to this numerical problem, please look very carefully whether you have been asked to find out the work done by the agent or whether you have been asked to find out the work done by the field. The work done by the field will always be the work obtained, and whereas work done by the agent will always be the work done. Hope this particular video will give you another good insight in solving numerical problems related with the dipole, especially the torque experienced by the dipole in the electric field, the potential energy of the dipole in the electric field, and eventually the work done in rotating the dipole inside any electric field, friends. Thank you.